Well, hello class, and welcome to our first video lecture. This is going to be our third lecture technically in Chapter 10, and I will be doing screen captures of the computer from time to time, and we'll post them on Canvas. So let's start up, and a refresher here. Let's review. Oops. N is the number of nuclei of your material at time t, and 0, of course, is the number of nuclei at time t equals 0, right? We call lambda our decay constant. Which is essentially in the units of numbers per second, decays per second. Or per time interval. We have minus dn dt as the decay rate. We also define something else, the activity, as the absolute value of the decay rate, right? Because the decay rate is technically negative because you were losing nuclei. So it's, we'll just write it as dn dt. Let's see, the other relationships we had. Well, we knew, or we showed that the number of nuclei existing at time t in terms of the number of nuclei at t equals 0, or the starting of our time period, is n0e to the minus lambda t. Right, so that's definitely worthy of boxing in and remembering that specifically. We define the half-life. T sub 1/2 is our half-life. And that is essentially the time for 1/2 of the nuclei to decay. And you can determine that in terms of your decay constant out here by specifying that n equals half of its original value at t equals your half-life value. It's found out essentially that the half-life and the decay constant are closely related, and we get that lambda, the decay constant, is equal to 0.693 over the half-life. And the units used for the half-life will determine the units you get for the decay constant. So if we know the half-life, we can get the decay constant. That's important. Knowing t sub 1/2, we can get lambda. Okay, if you take a look at what the activity is, just its definition as the absolute value of the decay rate, we can define our activity this way. It's dn dt, and well, from our initial situation we said dn dt is equal to minus lambda n. solve that differential equation to get n as a function of time. So we know dn dt, we can actually do dn dt, take your derivative of this, and you'll find out, well, it's exactly what we expect. It's lambda n, and n is a function of time, so let's insert that, lambda n0, and our decaying exponential. Okay. From that, well, our initial activity is just our decay constant times the initial number of nuclei. So activity at t equals 0, or at the starting of our counting. Cool. And so then we can write the activity, and you can just do it by direct substitution. Lambda n0 is right here, and so as shouldn't be a surprise, your activity decays exponentially, right? That's important because that's how we're going to talk about measuring the age of a sample with a given amount of radioactive nuclei remaining. Last thing to note, and this is relatively new, this isn't a review, in fact the activity is new, and one last thing is our lifetime. So t with a bar over it is defined as the lifetime, and it's just the average time that a nucleus will live before it decays. For a nucleus to decay. And it's going to depend upon the activity and the type of substance. And it turns out, and you can sort of make the argument pretty quickly, that it's just the inverse of your decay constant. Okay, so hopefully you have these all jotted down now. And I'll just take a quick screenshot of that. Okay. Into a new window here. And I'll add a blank. And good. Now we start. So what I want to do is follow an example similar to 10.4. So you could play around with example 10.4. I figured I'd do it for a different material. And it goes like this. We want to find the decay constant and the activity of promethium-146. Promethium. So I just wanted to find something interesting. So it has an atomic number of 61. Maybe you can't read that. Let's try that again. 146, 61 promethium PM. And given that we know its half-life, its half-life is equal to 5.53 years, right? So take a sample of promethium-146 and wait 5.53 years and come back to it, and you'll find out half of the promethium has decayed away into some other isotope. Okay, so to find the decay constant, well actually let's do that. No. Find lambda and activity for 1 gram of that substance. So the decay constant Seems I can do decent in cursive here, not great. Well, remember, its definition. It's really negative natural log of 1/2, but if you take that value, positive 0.693 over your half-life, right? And if I just go ahead and do it in years, well, I'm going to give myself a break and convert to seconds. 0.693 over 5.53 years. Right, so right now this is technically decays per year, but we're going to convert. And if you do your calculation, 60 minutes, 60 seconds times 60 minutes times 24 hours times 365, blah, 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 you'll find roughly it is 3.16 times 10 to the 7th seconds per year. For 1 year per that many seconds. Do the math. Into 4 sig figs, you get 3.966 times 10 to the minus 9, and that would be technically decays per second. Without this, it would be decays per year. It would be even smaller, right? Okay, so there. Done. Easy enough. B, we need to basically find out in 1 gram how many nuclei are present, right? Find the number of nuclei. Of 146.61 promethium in 1 gram. Right, and so we need basically our molar mass. Is needed. And if you go to various tables, and it's all over the web, you should be able to find that the mass of 1 promethium-146 atom, essentially, is, what is that number? 145.9 atomic mass units, right? Or its molar mass, and this is just my way of describing mass per an atom of versus mass of 1 mole. Its molar mass is therefore 145, let's fix that, 145.9 grams per mole. Okay? In 1 gram, we have basically the number of nuclei well, if we know it's 145.9 grams per mole, and we know we have 1 gram, what fraction of a mole do we have? Well, that's 1 gram divided by 145.9 grams per mole. So 1 over 145.9 moles, right? 145.9th of a mole. And if you take that and you multiply by Avogadro's number, right? 6.022 times 10 to the 23rd number of them per mole. And you can see here grams over grams per mole becomes mole. How many moles? Well, 1 over 145.9. Multiply that by the number of atoms per mole, and you get the actual number of atoms. That comes out to be 4.1275 times 10 to the 21 nuclei. of promethium, 146. Okay, we're almost there. If this, well, we assume, oops, that's interesting. We assume, at t equals 0, because the activity is always going to change and it's going to decrease, we want to know what is our activity at this instant of time with 1 gram of stuff. You know, as soon as we collect 1 gram and start time off, next thing we know, we have less than 1 gram of these nuclei, and we're converting to a different material. So at time t equals 0 is really what we're interested in. And if you consider that, your activity at t equals 0 is just lambda times n0. And this is technically n0, because this is the number of nuclei I'm going to have in 1 gram. And as soon as I collect them together, they're going to start decreasing as they decay. So we have our lambda value of 3.966 times 10 to the minus 9. Decays per second times our n0 of 4.1275 times 10 to the 21 nuclei. And together, that gives you an activity of 1.637 times 10 to the 13th decays per second. Pretty interesting. One last content thing to think about here. And that has to do with the exponential decay of your activity. If A equals A0 e to the minus lambda t, and you go ahead and ask, what is A at the time of 1 half-life, shouldn't be a big surprise what you get. Let's input that. The activity at 1 half-life of time is equal to your initial activity. But remember, lambda is your decay constant, and in terms of your half-life, it's 0.693 over your t sub 1 half. But the time, that was your lambda, your time here t is t sub 1 half. And if you check out and do the math, you get A0 over 2. Right? And so after 1 half-life, the activity has also become half its original value. Activity is halved. Pretty interesting. Not a big surprise. So we'll end this video here and we'll start up the next one.